Photoelectric effect, make sure you know the definition, is the ejection of an electron from the surface of a metal or other material when light shines on it. And Einstein proposed that light consists of quanta or particles of electromagnetic energy called photons. So photons are particles of light, just like an electron is a particle of, in an atom. Inside the atom, it has a charge, a negative charge associated with it. A photon is a particle of light. So again, this is what he said, reinforcing what Planck said. And the energy of the photon is proportional to its frequency. So here is the equation right here. E equals h times nu. Tell you what h is in a second. But actually, let's look at this diagram and then this very important statement. It says each electron is struck by a single photon. In order for you to eject electrons from this material, and it's a metal, you notice that it's not ejected when you shine red light. But it is ejected if you use green here and this darker, I'm not good with colors, this bluish color. So, because again, these are more energetic than red, as we looked here. Okay, red is closer to the right side, which is less energetic because they have a longer wavelength. Well, you can tell that they have a longer wavelength, which means less energy. So be able to relate this. So again, only when the photon has enough energy will the electron be ejected from the atom. That photon is said to be absorbed. So let me show you a quick simulation of this. All right. So you have a metal here, it's potassium. What am I shining on it? If you can tell, this is red. Red photon at the wavelength that is corresponding to the color red. And if you notice that no electrons are being ejected. Well, if I lower the wavelength, I'm going to increase the energy. So observe what's happening to the color. Still, no electrons being ejected. So I'm going to just go, so notice now, I have electrons being ejected. That is the photoelectric effect. That photon has to have enough energy to eject all those electrons. Otherwise, you cannot, the photoelectric effect is not valid unless it satisfies that criteria. So going back to the equation. Right here. This equation, which says E is energy equals H is Planck's constant, and it's 6.626 times 10 to the negative 34th joules times second. It's a constant, so it's always available. Just be able to use this equation in both forms. So here it is, Planck's constant, the frequency, based on what Einstein told us, equals, now in the other form is that Planck's constant times the speed of light over lambda. If you recall, this comes from this equation, which is the equation we did at the beginning, C equals frequency times lambda. So if I solve for, I want to substitute for the frequency, it's going to be this. So this part right here is, use a different color here so you can see it, is this substituted right here. Okay, so let's do a calculation on this. The red spectral line of lithium occurs at 671 nanometers. Now, it is given to you here in meters, but be able to convert on the test if I give you that. Calculate the energy of 1 photon of this light. Just 1 photon, small amount of energy. Okay, so let's discern which equation we should use. This form or that form. Well, let's see what's given to us. What's given to us is wavelength. So it must be this form, not this form, because this one I would need the frequency. So therefore, it's going to be E equals, that's the energy, H times C over lambda. So let's plug in. H is right here, 6.626 times 10 to the negative 34th. Sometimes it's written as 6.63, by the way, for rounding. They rounded it up. So times the speed of light. This is a constant. If you look back at the beginning, times 10 to the 8th. Meters per second over, this was given to us converted, but be able in the future to convert from nanometers to meters and vice versa. 6.71 times 10 to the negative 7 meters. So here's my calculator. .626 exponent negative 34th times 3 exponent 8th, close parentheses, divided by 6.71 exponent negative 7. Here it is. I need 3 sig figs, so I get 2.96 times 10 to the negative 19th. And what's the unit? What's the unit of energy? It's joules. Cancels, the seconds cancel out and the meters cancel out. So you're left with joules. Here it is. And by the way, these are the only calculations that you're going to do in this thematic unit, which is quantum mechanics all the way up to bonding.